Bivariate analysis is the study of relationship between two variables. Now, as the name would suggest, bivariate, it clearly indicates we are including two variables in our analysis. And this might actually introduce you to three different scenarios. You might have a scenario where you're trying to understand the relationship between two numeric attributes. Another scenario where we would have one numeric and the other categorical variable. Or the last scenario where both of them could be categorical. So what statistical measures do we use, or what kind of data visualization techniques we can put in place so that we can interpret the relationship and study what kind of patterns exist between two variables while analyzing them? So we'll start with numeric and numeric variables. So the easiest way to visually interpret two numeric attributes is using a scatter plot. A scatter plot defines the correlation between the two numeric variables. So correlation is a simple statistic measure. We call it as correlation coefficient, and is used to measure the strength of relationship between two attributes. It's a number which takes a value between -1 and +1, where +1 would be strongly positively correlated and -1 will indicate strong negative correlation. The example showcased over here might not be really intuitive, so I've taken the same example which we used in the previous slide. So we're trying to understand, using a scatter plot, the relationship between satisfaction level and last evaluation. So you don't really see any trend over here. So you can't conclude whether it's a positive correlation or a negative correlation or is there a relationship between them. It just looks a random mess. So just to make things simple, I'll try to demonstrate a simple example using the visual tool which we have over here. So consider we have a simple chart, a plot. We are trying to plot two variables, x and y, both are numeric, and you might see an increasing positive trend. Like, let's say you're trying to plot a simple example of, let's say, number of years of experience, this would be work experience, and the annual salary package for that employee. And you would actually expect, as per the industry trend, with more number of years of experience, you would actually see people earning more salary, right? So it is kind of a linear trend increasing in a very coherent fashion. And there definitely might be exceptions. There might be a person with less experience but earning really high. There might be someone who is really high experience but then doesn't really earn a lot, and then so on. But then overall, if you take a look over here, we can just have a basic visual overview to see that there is a kind of an increasing trend, right? So this is called a positive correlation. And this when we calculate the correlation coefficient, it would kind of be somewhere between -1 to +1, -1 to +1. And in this scenario, we might expect, let's say, something like 0.75 can be indicated as a really good coefficient. So 1, which indicates perfect correlation, is actually an ideal case. You'll never find a variable which should actually have perfect correlation. So anything between 0.75 is actually a very strong indicator of high correlation. On the same note, consider a scenario where you have negative correlation. So you take two variables. Let's say x would be an indicator of weight and y would be an indicator of number of years lived. This is a hypothetical example, so please don't take it seriously. A typo over here. So it's generally observed that the more weight you have, or the more obese you are, the more kind of the more diseases or disorders you are a victim to, and generally it would translate to a less healthy lifestyle or a lower number of years of life. So if you try to make a simple plot over here, let's say let's say this would be 50 over here, and this would be 100. We just can't start at 0, right? Someone who's really healthy, we might say that he's going to live for more number of years. Someone who's a little more heavy or obese is going to live slightly less amount of years, and so on. This is a hypothetical example, and we might see something like this. We'll definitely see exceptions. We'll have someone who is performing in a different way. Someone who is obese but still has a very healthy lifestyle, and so on. So kind of you can expect a lot of out of the box cases, but then at a high level, you can kind of observe that there is a decreasing trend, which means that there is a negative correlation, which means that as weight increases, the other counter variable decreases, right? A negative correlation exists over here. So this might, let's say we have -1, 0, +1. You might find a negative correlation values tending towards this section. So that, let's say -0.05 would indicate a highly negative a very high negative correlation between the two variables. Again, -1 is a very ideal case. You won't really find that. Now, in some cases, you might really have a relationship between both of them, but then two variables, but then looking at the number or the correlation coefficient, you might not be able to interpret whether there is any sort of relationship between the two. We'll get into this use case when we come to the programming exercise for bivariate analysis. So just after once we cover the explanation for the three different use cases, we'll actually get into the programming perspective example, and that's when we'll actually discover another scenario where just interpreting the correlation coefficient might not really suffice to understand whether there is actually a relationship between the two variables. So let's get back for now. We look into numeric and categorical use case. So what do we do over here? We have a simple bar chart. And the bar chart is used to showcase the average values of a numeric attribute across the different classes of the categorical attribute. So we've taken again a hypothetical example over here. This is again from the data set. So we'll say salary, which has 3 levels: low, medium, and high. There is a typo over here, please ignore that. And across average satisfaction level. So average satisfaction level is the numeric attribute, and salary is the categorical attribute. What you're doing is you're aggregating the numeric attribute across the levels for the categorical attribute. I can see that, as you expect, high, which means that high band salary employees generally have a higher satisfaction level than the counterparts of low and medium. So we expect an increasing satisfaction level across the salary bands, and we kind of see that. But if you observe closely, you can see that the difference is, even though visually appears very high, it's actually pretty low. So it's 0.6, around 0.62 and 0.63. That's bare minimum difference between the three. But since the y-axis is organized with a different value, like it starts at 0.58 and ends at 0.65, so it's zoomed unusually high, and we get perspective which we don't really expect to comprehend the right way. So we look into Python example. So this is an output which we create from Excel. When we look at an example from the Python's matplotlib or pandas library, we get a better perspective to understand. How these two variables behave. So the last scenario we have, and one thing before we move on. So in this scenario, the aggregation metric might not necessarily be average or mean. In some cases, it can be sum, FUN sum, or it could be the maximum value or the minimum value or something else. It could be completely driven by the use case. But then by a general rule, you can actually say that most of the use cases, you'll always use average as the metric to aggregate across the different categorical levels. The last scenario, when we have both the variables as categorical. So what do we do over here? We actually look into the frequency distribution of one categorical variable across each level in the other categorical variable. So in this example, again, we've taken a very simple example. We're trying to understand the distribution of salary segments across the sales department. So sales department has different categorical levels like sales, accounting, HR, technical support, and so on. And we're trying to see the percentage of different of the employees within each of these bands, which is belonging to the salary bands across each level. So you can see that sales has approximately 50% in the band low, then another 40% in the band medium, and then around 10% in the band high. So on you can go. And if you take a better perspective over here, you just take a closer look, you can see management kind of looks different. So just using a simple visual inspection, using a stacked bar chart, you can actually look into the distribution of one categorical attribute across each level of the other categorical layer. Now, in this scenario, we've taken a percentage distribution. So we might not necessarily take percentage distribution across all the scenarios. In some cases, a simple frequency plot will also do. So instead of percentage distribution in the stack bar chart, we might have a simple stack bar chart of frequency counts. So this was how we do bivariate analysis. So we have understood what measures, statistical measures, do we take into account while we go ahead with bivariate analysis, and depending on the scenario of the kind of variable you're encountering, what kind of visualization tools would you use should help you to interpret or study the relationship between two variables of interest. So let's look into an example using Python code. I'll jump into Spider. Let's just print the different column names that we have in this data frame. Now, if you look over here, sales, which indicates different departments in the company, salary, which defines the different segments of salary, and left, which means that the employee leave the company, yes or no, which could be indicated as a 1 or 0 flag, and work accident might also be a flag like 1 or 0. Rest all of them are actually numeric variables. So satisfaction level, last evaluation, number of rejects, average monthly hours, these are all numeric variables, and we have 3, or primarily we can just focus on 2 for now as categorical variables. So to just take into account a simple example, we'll explore the 3 different use cases where we have numeric and numeric, numeric and categorical and categorical with this dataset itself. So first we'll start with a simple categorical and categorical explanation. We'll take sales and salary into account. So in sync with the explanation we just had right now, what we would do is we would do a simple frequency plot using a stack bar chart. Now we need to transform the data to actually be able to understand what is the frequency distribution of one categorical variable across each of the levels present in the other categorical variable. So let's go one by one. We'll start with the sales department. So df, we access the series or the column called sales, and we can just type in unique, and this will print the unique values inside that column. So we can see, okay, fine, there are approximately quite a few values: sales, accounting, marketing, etc. What about the other one? So let's say we take the different unique values within salary. We already know the name, so but still we have low, medium, and high. Now we want to know what is the distribution of low, medium, and high across each of these levels. That's when we need to do a cross tab. Cross tab is analogous to the pivot tables, and pandas provides you a ready-made function to do cross tab. So we say pd, which represents the pandas object, dot cross tab. We pass in the first column of interest, that is sales, and we pass in the second column of interest, which is salary. And pandas will automatically create a cross tab for us in the easiest and neat format. Here we go. As we interpret this, we can have, let's say for the department technical, we have around 201 high paid and high salary employees, 1,372 low salary employees, and 1,147 medium salary employees. Now if you could actually do some more math, you can actually say sum 83 divided by 83 plus 609 plus 525 and calculate the individual percentages for high, low, and medium. But that is not necessary in all scenarios. Let's plot a simple bar chart to understand how do these numbers look like. Rather than going through and scanning each number, we can just simply plot a number and visually understand where do we have the highest distribution. So again, to visualize, we have 2 methods over here. One is a straightforward method which we learned earlier using matplotlib, or you also have a visualization library inbuilt within pandas. So if you just call in after this function, let's say you say plot and pass in the parameter kind is equal to bar. The default one is line chart, and you execute this. Pandas will neatly create for you a simple bar chart. Now you can see, okay, majority of the distribution actually comes under sales, and within sales you can see that low is the highest. So majority of the employees come under this category level. So rather than scanning through all the numbers individually, you can actually simply out a simple bar chart and then quickly scan and analyze the numbers over here. But then we actually plan for a stacked bar chart. So what we'll do is we'll just add in one more parameter. Stacked is equal to true, and we can see here we have a stacked bar chart. If you want to actually create a percentage bar chart, I'll leave that to you. It's a simple switch you can actually add over here, or you can actually engineer the data and represent that using a stacked bar chart. But using this, you can clearly understand more about the two different categorical variables. You're trying to understand the relationship between two. So you can see that majority of the ones we have, majority of data actually falls under sales, and within sales we can see how are the different segments of salary looking like. One interesting thing, if you take a closer look over here, management, you can see that management has a good amount of ratio, a very good ratio between the three, like low, medium and high salaried employees. Almost all of them look like 33%. Like it looks fairly straightforward. Like if there's a clean division between three levels over here. But that is not the case in the other ones. Have a look over here. The blue one, which represents the high salaried employees, form a very small part of the entire chart. So this is how you actually visually inspect, interpret, and understand relationships between two different variables. Let's move on to the next example. You can actually do the same exploration using the matplotlib library also, but I would leave that to you. Please explore in your free time. Let's move on to understand the relationship between a numeric variable and a categorical variable. So I'll again just print the columns over here, df.columns, and I made a typo. Alright, so df.columns. So let's say satisfaction level would be our numeric variable, and we'll take salary as our categorical variable. Now we will need to augment the data to be actually able to go ahead with a bar chart. So if you remember, we need to aggregate the numeric attribute across each level of the categorical attribute. So if you remember in the data engineering exercises which we had in the previous module, we explored the group by function. We can do the same over here. Let's first create the data or augment the data in the right format. So let's just add a comment, numeric and categorical variable explosion. Alright, so let's say df, we say group by, and we pass in the group by index, which is in our scenario salary. So we want to aggregate across salary. What attribute do we need to aggregate? We need to aggregate satisfaction level. Here we go, and we pass in a mean function. So what you're doing basically over here is, if you have if you're finding it hard to recollect, you're finding the mean of satisfaction level across the different levels of salary. Now if you execute this, you can see that we get a simple plot, no, not a plot, we get a simple tabular format display for each of these values within salary and the corresponding mean satisfaction level. And the numbers are in sync with the example which I showcased in the PPT. You can see that low is 0.60, medium is 0.62, and high is 0.63. So the differences between them are fairly low, but then rather than just using these numbers to consume your insights, you can just do a simple plot and you can say kind is equal to bar. It will help you visualize the data using a simple bar chart. And there we go. Now, since the y-axis is more well tailored, it starts at 0, it ends at the maximum value, it's easier to understand the true relationship across the different levels, because it looks like, okay, fine, there isn't much difference. But had you fabricated the y-axis or had you zoomed into it, it would have kind of revealed some spurious insights. So this looks better. We're trying to understand the relationship between a categorical attribute and a numeric attribute using an aggregation metric of average across the different levels. Now, again, like I already mentioned, you could do the same using matplotlib, but then I would leave that exercise to you to explore on your own. Now we come to the last part, which is another interesting part in bivariate analysis. Here we explore two numeric attributes. So both of them, numeric attributes, we can actually understand the strength of these two numeric attributes using the correlation coefficient. So pandas by default provides you the correlation function. You say df.cord. Now rather than passing the attributes over here, what you can do is you can just say df.correlation, and correlation function will get into the depth of ds data frame. It will look into all numeric attributes and then give you a cross tab of all of them. Let's just explore this. You get a bunch of numbers over here. So as you can see, I had a cough. So the correlation between satisfaction level and across all the numeric attributes that is found in the data set. So left and work accident might actually be categorical variables, but then they are stored in the data set as 0 and 1. So accidentally pandas misunderstood that as a numeric variable. But then just ignore that. So you can see the satisfaction level across all of them. You can see the correlation coefficient. Now the correlation coefficient between satisfaction level and satisfaction level, that is between them itself, will always be 1. That's a perfect relationship, right? So you can see that trend everywhere. So time spent with the company and time spent with the company, it's 1. Now, if you look over here, you can actually go ahead and simply understand which two variables have a strong correlation between them. Now, if just a basic scanning through all of them, I don't really see something really very interesting. No, so this one looks fairly interesting. I would say number of projects has around like 0.41 correlation with average monthly hours. It kind of makes sense using the business logic, but then 0.41 is not really very strong correlation, and I'm sure the plot might also not look very neat. So here I'll just use the matplotlib library as a tlt.scatterplot, and I'll pass in the x and y variables. Let's pass df, and I'll pass, let's say, number project. I need to add this, yes, and I'll pass a second variable, which would be time spent with the company. Now if I look over here, I do a simple plot, and I don't see any interesting results. Like, this just doesn't make any sense. Let's try a different variable. Let's say number of projects, time spent with the company, and average monthly hours. Do we have a relationship over there? Not really. We don't really see anything interesting over here. So like I already mentioned, so while we're exploring bivariate analysis, the first part, like we're understanding what is correlation coefficient, I mentioned that if in case you find a correlation coefficient of 0.01 or 0.1, just looking at the value, you might tend to discard that because you assume that there's no correlation coefficient. There is no really any sort of relationship between both of them. But then it is actually important to visually explore using a scatter plot. I mean, try to understand the relationship between two numeric variables. I'll give you an example using the visual tool as a demonstration to help you understand how this works out. So if you consider an example, let's say that we have something similar to this one, like you have most of the points kind of in an increasing fashion. This is a strong positive correlation, and your number will also be representing the same. So let's say I'm just giving a random number here. So let's say you have a correlation of 0.8, and this sounds pretty strong correlation. On a similar note, let's explore a scenario where you have strong negative correlation. So something like this, where you have multiple points kind of revealing a negative downward trend. This will also be a relatively strong negative correlation. And if you try to calculate the correlation coefficient, you'll fairly find a strong number, like let's say minus 0.75. This is just a random number, just for illustrative purposes. But then consider a scenario where you have a plot like this. You have an x and y variable, and you find something very interesting. So the trend increases to a certain point, but then after some point it kind of starts decreasing. So you have a non-linear relationship between the two. Now this is kind of increasing first and then decreasing. So this is like a non-linear relationship. Now if you go to calculate the correlation between x and y over here, what happens is the increasing trend kind of negates with the decreasing trend, and both of them counter each other, and you get a very low correlation between both of them. So you might get a correlation of, let's say, something like zero point 0.1 or 0.2, extremely low value. So just looking at the number, you might actually miss out that there is actually scope for a relationship, and there is some sort of relationship between the two variables. Now, there are a couple of correlation coefficients which while calculating the relationship, takes into account a non-linear relationship also. But then the default one is in our Python doesn't really take care of that. So I would recommend you to go and explore this on your own. What kind of correlation coefficients techniques that are implemented in Python account for non-linear relationship? Or let's just consider that you have two variables, x and y, and there is a relationship between them, but it's a non-linear relationship. That is, they might, like let's say the best example over here would be x would be age and y would be strength. So towards a point, and let's say this is like 10, this is 40, and this is 80. So while you grow till 40, you would have really good health, but then after that, it kind of gets tarnished. So you see a relationship which definitely exists, and it's definitely a valid one, but then it's a non-linear one, and then you need a correlation coefficient which actually takes into account a non-linear relationship. So there are a couple of them. I would recommend you to please explore them on your own. So that's about the different bivariate techniques that we have explored till now. Let's just get back over here. We've explored, yeah. So we've explored what is bivariate analysis, what are the different scenarios that we need to consider. So two numerical variables, one numeric and one categorical variable, and probably two categorical variables. So what kind of statistical measures do we use to understand the relationship between the two, and what kind of plots or visualization techniques can be leveraged to study the relationship between the two. So just like univariate analysis, we've understood bivariate analysis and the kind of possibilities of exploration over here. So the next thing, which is multivariate analysis, is an extended version of bivariate analysis. A linear regression would be a classic example of multivariate analysis. But then we'll be taking up that in more detail in the next module, machine learning. So for now, we'll take a break over here. We take a pause and we stop with bivariate analysis. And we would move on to another important topic, which is feature engineering. So that's all with this topic.